To demonstrate some of the forces involved, I've relied on the powerful magnetic field of a permanent magnet. But because, as I explained earlier, there are forces that are generated by the current, if you get enough current, you can actually produce very significant forces. And so what I've done is I've set up a little demonstration here using a power supply to charge a rather large electrolytic capacitor. This is a 4700 microfarad, 450 volt capacitor. And this capacitor is going to be discharged or shorted through what's called a pancake thyristor, or an SCR. These are rather unusual solid-state switches that can handle extremely high voltages, thousands of volts, and can handle tremendous currents, tens of thousands of amps. And the way they work is you effectively charge or allow current to flow through one side, and then there is a small gate that is switched. And the way the gate works is that there is a small bias voltage that I create between the ground of the thyristor and the upper voltage that's produced by the 3 volts from the battery. So effectively, by providing 3 volts above ground to the discharge end of the switch will then open and allow all of the voltage and all of the current from the capacitor to discharge through this loop I have formed between these 2 narrowly spaced conductive rods back down to ground. What we'll do is I'll demonstrate this and show that you can get noticeable forces generated if you develop sufficient amounts of current. And we're going to start charging the capacitor. This is the bolts DC across this capacitor as the power supply is charging it. We'll go to about 50 volts or thereabouts. And then when I push this button, I will close the switch and will allow the current to go through the 2 conductors. Watch the 2 parallel conductors. 1, 2, 3. You see they moved apart. The connector at the end was also feeling a force. It wanted to move this way, but it's tethered by the weight of the leads. The current output from this capacitor is proportional to the voltage. The current, the energy, is proportional to the square of the voltage, but the current is proportional to the voltage. The forces between these rods, however, is proportional to the square of the current. The field in one interacts with the field in the other. So if I double the field here and I double the field here, I get 4 times the force. So if I charge the capacitor up to, say, 100 volts or twice as high, I get 4 times the force between these 2 conductive rods. Once we get this up to about 100 volts, then we'll hit the switch and you'll see what the difference is. 1, 2, 3. Substantially different. Now, these are the same forces that are used to operate a railgun. And one of the interesting things is that the current that is flowing through here is actually pretty substantial. It's on the order of thousands of amps. And I'm going to demonstrate exactly what that is with an oscilloscope. Okay, now I've set up the oscilloscope, and what we're doing is we're measuring the voltage across the capacitor, and when we triggered the circuit, we'll show the decay of the voltage across the capacitor as it goes through the dead short. One of the things about these capacitors is that they have a fairly high internal resistance. So it's really the capacitor itself that limits the discharge speed, not these wires. This is significant, as I'll explain in just a second, but what we'll do is bring this up to about 100 volts. And when I fire this on 3, you're going to see a tracing of the voltage that goes across those 2. 1, 2, 3. Now, if you see on this scan, the voltage has decayed to about 30% of its initial point. And these are 50 microsecond grids in approximately 100 to 150 microseconds. Now what that means is that almost all of the energy of the capacitor has been discharged within about 1/6,000th of a second. And that's significant because The two ways that we're going to be going with this information is we're building a very large yoke-style magnet to produce a much higher field than the ones that you've seen in these little test devices, to produce a much more powerful MHD pump, as well as a much more powerful MHD generator that will operate on seawater. In addition, what we're going to be doing is using some of this technology to build a railgun. The principles of a railgun are very easy to understand. I mean, we've just gone through that. But there are two very, very difficult problems that have to be solved with those devices. The first one is that when a railgun fires, the pressures that you see here, which are microscopic based on a few thousand amps, are multiplied thousands of times. And the forces that are pushing the rails apart when a railgun fires are measured in thousands of kilograms. The sliding armature that goes between the two rails has to make almost perfect contact but have almost no resistance. And as you can imagine, that would be extremely difficult to do, because if you have just a little bit too much resistance before any load has been produced, as the projectile or the armature that you're going to be sliding can lock up. And when it does, all the current will flow through it, it will weld in position, it will probably blow up. And if you have enough clearance that it's able to get through, what will happen is under the forces of the discharge, the rails can move microscopically apart. You'll get an air gap. You'll develop arcs and plasma and waste a lot of power and potentially, again, blow up your armature. So one of the techniques that we're going to be using uses the same thing that I demonstrated with the liquid metal. We're going to use a liquid metal sabot to help provide good contact with relatively low machining tolerances. The US military has released information that they were researching this early on. Russian researchers have put out some papers, and the comments are, this looks very promising, but it could be kind of expensive. I don't think that that should be a limitation, at least if the process works, and so we're going to try that. The second aspect of this is that you'll see, if you watch a few YouTube programs or YouTubers that are trying to build railguns, they will frequently take a large number of these capacitors, they'll wire them up in parallel, and then they'll use the armature itself as the switch. It's providing the discharge. As I demonstrated, this 4700 microfarad capacitor, which at about 100 volts is storing about 25 joules, will discharge almost all of its power within about a 6,000th of a second. If you imagine a railgun that's, say, about half a meter long, if the initial velocity of the projectile is close to zero and the final terminal velocity is what's ever coming out of the gun, the average speed of the projectile is half that. So if you travel half a meter in 1/6,000th of a second, you're essentially traveling at a speed of roughly 3,000 meters per second on average, and a peak speed of 6,000 meters per second. That's orbital velocity, far higher than any railgun fires. So the problem with discharging these capacitors straight through a dead short is that you end up utilizing all of your power very early on, generally welding your projectile or blowing it up, and not getting the power out when you need it. What you need is to use what's called a pulse forming network that essentially gets all the power out of the capacitors that you can, but not any earlier than the projectile leaves the end of the gun. And a pulse forming network introduces inductances to slow down the pulse and tailor it to the length of the time of flight through the rails. In addition, almost all of the YouTubers that have done this, as I said, dead short these electrolytic capacitors through these rails and through their projectile. When they do so, they create tremendous inductive fields, as we've demonstrated here. And those inductive fields, as soon as the voltage drops in the capacitor, will then refeed the capacitor in the opposite polarity. And this sort of refeeding will continue until the capacitor reaches a certain voltage, and then it will again feed back into the field. And this sort of up and down voltage reversal across the capacitor is called ring down. And that ringing in a polarized capacitor is lethal, So it's surprising that any of them survive more than one pulse, but they certainly wouldn't survive many. And that's one of the reasons why you want to use a thyristor or a rectifier to protect the capacitors in the process of building the railgun. So as we move on with this project,